Okay, chemistry students, now we're getting into the really fun stuff. This is lesson 4.6, where we're going to look at quantum numbers. Each electron has a set of quantum numbers that will tell you where in the electron cloud it is likely to be located at any time. So we're going to take a look at the rules for determining quantum numbers, and you're going to hopefully see that the periodic table's layout kind of has a lot to do with quantum numbers, and so once you understand that, it makes kind of picking out the quantum numbers much simpler. So this would definitely go with chapter reading section 6.3, and I would highly recommend you read that as well. So here are the objectives for today. First of all, we want you to learn the four quantum numbers. They're designated N, L, M sub L, and M sub S. We'd like you to be able to identify possible values for the four quantum numbers and identify the four quantum numbers of an element's outermost or last electron. So let's get started.
Alright, so first thing I'm going to do is construct this table in your notes. I suggest hitting pause as we're going to go through this as fast as we can. You can pause us, so pause us when need be. So the first quantum number is the principal quantum number with the symbol of N. Its value range is 1 to infinity, which is normally also just 1 to 7 is the most common. But
yeah, realistically, the elements that we actually know of only have electrons out to about the 7th energy level. So theoretically, the energy levels go out beyond that, but in practicality, at their ground state, first 7 energy levels are the only ones occupied by the elements we know of.
All right, the next one is the sub-level quantum number. It is the symbol L, and its values are 0 to n minus 1. The 0 would stand for an S sublevel. So remember, that'd be the spherical orbital, stands for S. The 1 would be a P, 2 would be D, and 3 would be F. And we're going to go over some examples at the end to understand that better. So for example, real quick, if we had n equals 1, we would know L would have to equal 0. It's n minus 1. 1 minus 1 is 0. Okay, the next quantum number, we'll give examples at the end there, Mr. Ferguson. The next one is the orbital quantum number, where it's M sub L. This range is negative L to L. So if you had an S, the L would equal 0. And the M sub L would also equal 0.
So numerically, what we're saying is there's only one ever one S orbital.
Yeah, because it would be 0 to 0.
So there's only one allowable S orbital.
Yeah, so for P, L would equal 1, as we know from up front. So M sub L would be negative 1, 0, and 1, also shortened up to negative 1 to 1. So that would give us a total of 3 p orbitals, your px, your py, and your pz. Next is your d, and it's L equals 2, and it'd be negative 2 to positive 2, which would give us 5 d orbitals. If you remember from that page 32, there were 5 different d orbitals. And then lastly, he doesn't have space for this, but if L equals 3, so for F...
We'll squeeze it in up here.
Right, so for F, L equals 3. And then M sub L would be negative 3 to 3, which would give us 7 orbitals.
So this tells us how many orbitals there's going to be associated with each sublevel, which matches what we already told you in the last lesson.
And we can use a periodic table to figure out all these quantum numbers. And lastly, real quick, is the easiest one. It is the spin quantum number, which is known as M sub S. And it only has 2 values, either plus 1/2 or minus 1/2. And what that means is it's just giving us the spin of the electron. Is it spin up or is it spin down? So that gives us our 4 quantum numbers, and now we're going to practice on the next page getting these quantum numbers, so please get a periodic table out at this point, and we'll start some practice.
And you're probably going to want to look on what page is that in their packet, 31, which has the same graphic that we're about to show you.
Yeah.
One other note before we go on, an orbital, we talked about an orbital quantum number. An orbital is basically capable of holding 2 electrons, which when we get into electron configurations, you're going to need to know that.
Exactly. All right, next slide. All right, so this is the graphic you will see on page 31. It is quite messy, but it talks about everything that we just went over. It goes through n equals 1 to 7. It does L equals n minus 1. 0 to n minus 1, I mean. It does m sub L, negative L to L, and it also does plus or minus 1/2 spin, or m sub S plus or minus 1/2. So let's look. It is a
little overwhelming.
It is a little overwhelming.
We'll break it down one thing at a time.
So let's look at the n. So n equals 1. Highlighter there. N equals 1 is this entire first row. There's no helium written over here, but that is the first row of the periodic table. And then n equals 2 would be the second row, n equals 3 would be the third row, n equals 4 would be the fourth, etc., etc., etc. So then we want to move on to the L quantum number, which is n minus 1. So if we're in...
the gut ranges from 0 all the way up to n minus 1. Yeah. So for the S sub-level...
the first 2 columns of the periodic table are your L equals 0, or your S orbitals.
So basically, I know that the last electrons, the outermost electrons in any of these elements are in an S orbital.
S orbital. And then if we had an L equals 1, we're talking about the P orbitals, or the P block, which is the last 6 on your periodic table. It tells you that the P block holds 6 electrons, because you can see there are 6 individual squares. It tells you that there are 3 different P orbitals, Px, Py, and Pz. And it also gives you an idea what the shape of the orbital looks like, if we know what a P orbital looks like.
So, and if we were called on an element in this block, then we would know its last electrons are going to end up in one of these P orbitals. So if it's in this row, it's going to be in the 4P.
Yep.
4P sublevel, whatever orbital it's in.
And then L equals 2. You notice it goes from negative 2 to positive 2, and it goes through it twice. I didn't put it on the other one, but the L also does plus or minus 1/2, negative 2, or negative 2 to 2, and minus 1/2, negative 2 to 2. That gives us our 7 orbitals. And then we know anything that's in this region of the periodic table, known as the transition metals, that we'll find out later, is a D block orbital, and L equals 2. Lastly, L equals 3. You see it goes from negative 3 to positive 3. That gives us our 7 orbitals.
And then it repeats again.
And it repeats again because it's minus 1/2. So those are your L's. The next would be your M sub L, which would be your, in the case of the S block, there would be 0.
Just M is 0. Here M is the
negative 2 to positive 2.
Positive 2, then
and it repeats.
2.
And then the M sub S is what causes it to have that split in the repeat. So plus 1/2, minus 1/2. It's just something you kind of have to look at and get used to. So instead of us talking about it a lot more here, I think it would be helpful to start looking at some elements to get the quantum numbers for specific elements. So keep page 31 out, get out a periodic table, and I think we're going to go through some practice for you here. Alright, so here's a periodic table. First one we're going to pick, let's pick an element at random, let's say beryllium, just because. And we want the 4 quantum numbers of beryllium.
Okay, so I'm just going to write N, L, M sub L, and S.
M sub S, technically.
M sub S.
There you go. So beryllium, what row is beryllium found on? Well, if we use your periodic table, you see it's in the 2nd row. So right there we automatically know beryllium's N equals 2. The second question is, what column is it in, or what block? Well, it's in the first 2 columns, which makes that the S block. So L
equals 0.
And that's because N minus 1, 1 minus 1.
There's only one allowable... well, no, there's 2 allowable orbitals on the second.
But the first one, since it's in the first column,
0. The
Yeah.
second one would be over there in the P block where boron and carbon and those
we
guys
aren't there.
We're not there.
And then M sub L, it's negative L to L. If L is 0,
so
then M sub L would just have to be 0 as well. Because that's just knowing our range. So M sub L is negative L to L, which should be 0 to 0. And then lastly, M sub S, it's the spin. So you cut the block in half. The left half will be positive, the right half is negative.
So since beryllium's on the right,
on the second half, it has to be a negative 1/2. So if you're sitting there saying, where did we get these numbers from? Go back to that table we had you write out and look at the ranges again, and then look at page 31. Putting those two together will allow you to do this. We're kind of giving you a postal address of each element through these quantum numbers.
That's very much a good analogy. It's like the address.
Exactly.
Each one of those numbers tells you one fact about where that would be on the periodic table.
All right, let's try 2 more practice, and then we're going to have a lot more practice tomorrow or in class the next day. So let's do, let's say, you want to do cadmium?
All right, cadmium. C, D.
N,
L, M sub L, M sub S.
Now I picked cadmium on purpose because we forgot to go over this in the last slide. But first of all, what row is cadmium in? So it's in N equals 5. It's right, yeah, right there. It's in the N equals 5 row. Now something we forgot to mention is that this is a D block. So it's still the energy, it's still the 5th energy level, but it is in, actually it's the 4th energy level, isn't it? Well, it's N minus 1 in those.
The D block is 1 back from
yeah,
the
so
row
technically
that it's on.
It's in the N equals 4, not the N equals 5. That's something we forgot to mention in the last slide. So do mention, or do notice that that it's in the 5th row, but since it's in the D block, it's in the 4th energy level. Now that's just something you're going to have to get used to, and the F block is similar in that it is 2 off of the row that it's in. But we'll cover those more in detail.
When we get to electron configurations, it'll make a whole lot more sense.
But just right now, it's just know that fact. It's in the 5th row, but it's minus 1 from the row it's in if it's in the D block. So the L, well, it's a D orbital, and D's would be a 2. Be a 2, because 0 is S, 1 is P, 2 is F. M sub L for this, we have to start counting.
Yep, it's in the very right-hand side, the last row, so it's going to be a +2.
Yep, so you can use your periodic table and line it up with your page 31.
Because it goes -1, or -2, -1, 0, 1, 2, and then that repeats.
And then you can also, since it's on the right side of the halfway point, we know it's a minus 1/2 spin. So really, this just comes down to you being able to use the tools given to you. So let's try one more practice. And what practice one do you want to do, Mr. Ferguson?
Oh, let's take arsenic.
I like arsenic. So,
poisonous.
Yeah, AS.
Okay, so we're going to start out by finding what
arsenic is right here. I circled that poorly, but you can get the point.
So now we're back online. We don't have to do anything weird like subtract 1 off because we're not in the D block.
We are in the 4th row, so N equals 4.
Principal energy level is 4.
L, since it's a p orbital, would equal 1. That's just general knowledge. L is going to have to be a lookup, so we know where arsenic is. It's in the 3rd column, so it has to be a +1. M sub L would be a +1, and it's on the left-hand side of the center. So that makes it a positive 1/2 spin. So these are the postal codes for these elements. Every element has a different set of quantum numbers. They can have 3 that are the same, but they cannot have all 4 quantum numbers the same. So that's something else to know. Every element has its own set of quantum numbers, and we're going to have more practice with this tomorrow in class. So enjoy.
All right. Okay, so your head might be swimming a little bit now, and that's normal. Don't panic. Here are two post-video questions. I tried to keep them simple because I know we're going to need more practice with this. Question number 1, what would be the n quantum number, that's the principal quantum number, remember, of the outermost electron in each of these elements? Helium, magnesium, and barium. So remember, the n one is quite easy to pick out if you locate the element on the periodic table, and you can really quickly spot the principal quantum number. Alright, question 2. So for electrons in the second energy level, that means n equals 2, principal quantum number is 2, what would be the allowable quantum numbers for the L quantum number? So I would look back at that chart or table that we made up on the very first slide after the beginning slide and see if you can spot that one. Be ready to discuss these when we meet again.